Here's a vector. In the coordinate system we're used to, we describe it as 2, 2, because we go 2 in one direction and 2 in the other. But let's change axes. Now we have one direction that stays the same, but the other direction is a different one now. These two directions still build a basis and therefore reach every single point in our space, but to reach the same point as before, we only need one step in this single direction. So this vector here, which is exactly the same vector as this one here, is now represented by 0, 2, because we don't go in this direction at all, but go 2 steps in this one here. Nothing about the vector itself changed. If I take it from here and drag it here, we see that they are exactly the same line. Only the way we described it changed. And this simple idea turns out to make complicated transformations much easier to understand. Hey, I'm Oliver, a computer science student and tutor. When I first learned linear algebra, I was confused by how the same vector can have different coordinate descriptions. That small gap made a lot more advanced topics harder to understand. So now I break down these core ideas into short, intuitive explanations to help you build a solid understanding for your exams. So in a prior video, I introduced bases as collections of vectors that allow us to represent any vector in the space. Now in our case, we are in the R2, so the two-dimensional space. And we can, in fact, reach every single point in space. This one here requires us to go 3 in this direction and 2 in this direction. And in the second coordinate system, it requires us to go 2 in this direction and 1 in this direction. A different basis requires a different combination of vectors to represent the same point, as we've seen in the introductory example. We are used to the standard basis, which builds the standard coordinate space. The vectors are 1, 0 and 0, 1 in two-dimensional space. And in higher dimensions, it's equivalent. All entries are 0 except for 1, for each of the n entries in the vector. So a total of n vectors in our basis, our standard basis. And we've seen that others work as well. So here we have the vector 1, 1 and the vector 1, 0. Which build the basis in this case. So since the basis for a vector space is not unique, we're able to use different bases to represent the same vector. We're not only able to simply represent these vectors in different bases, but also to translate them back and forth. So having the coordinates in this basis on the right here, we can, through a simple matrix vector multiplication, transform it into what the coordinates would be in our standard vector space, or our standard coordinate space. And the same can be done reversely. Given a vector in our standard coordinate space, we can apply a matrix vector multiplication to get to our coordinate space defined by the basis, given by these two vectors. Since we are able to go back and forth without losing information, this actually means that this operation is inversible, and you'll see in a second why. Here I have a formula that describes how to move from a specific basis to the standard basis. Here, our basis consists of the vectors b1 to bn, all having the size n. So from our prior video, we know that a basis for our vector space Rn needs to have n many vectors, and they have to be pairwise linearly independent. Thus matrix B, which I've written here, is now simply the collection of all these basis vectors as a matrix. So each one of these basis vectors has length n, and we align them as column vectors here, so that B consists in its columns of these basis vectors. As there are n many of them, and they have size n, this gives us an n times n matrix. And since these vectors are linearly independent, this means that the columns of this matrix are linearly independent, and therefore our matrix B is invertible. In our formula, we have on the left-hand side the standard representation of our vector. This would be in our example from earlier, 2, 2. So given the standard basis, 1, 0, and 0, 1, what the coordinates would be of that vector. Now this formulation here tells us that we look for what the coordinate description, or the coordinates of our vector v, are given our basis b. So what the coefficients would need to be for each of these vectors if we linearly combine them to get this vector v. In our example, this would be 0, 2, because we add 0 many of this vector here to too many of this vector here. Applying this formula to our example, for our basis b, which for its first basis vector has this one here, we enter that as the first column in our matrix, and the second basis vector as the second column. Then this is the representation of our vector in our basis b, so 0, 2, as written here. And doing this matrix vector multiplication, we exactly get 2, 2. So what we expected to get out. To move from the standard basis to a specific basis, so the opposite operation of the one I've written here, I will use the property of b, which I've mentioned before, that it is invertible. So what I'm able to do is multiply on both of these sides with the inverse of b. On the right-hand side, multiplying b with its inverse gives us the identity, and on the left-hand side, we get the product of the inverse with the standard vector. This matrix vector multiplication here finds the coordinates needed to build the vector from the basis vectors. So we know now how to convert a vector from its representation in one basis to the standard basis, and from the standard basis to a specific basis. But how exactly do we change from one basis that is not the standard basis to another basis that is also not the standard basis? We do this by using two steps. So starting from the coordinates in basis 1, to get to the coordinates in basis 2, instead of going the direct route, we model it as two steps, using what we already know. To convert our coordinates for a vector under the basis b1 to the coordinates under the basis b2, we go the indirect route of first translating it into the coordinates under the standard basis, and then in a second step translating it to the coordinates of basis b2. So this combines what we already know. From the coordinates under b1, we multiply with b1 to get the standard representation, and then multiply with the inverse of b2 to get to the representation under b2. Finally, we get this representation. V under b2 is equal to starting with v under b1 multiplying b1, and then the result, which is the coordinates under the standard basis, multiplied by the inverse of b2. And this matrix-matrix product is simply another n by n matrix. So this can be written as a single matrix, which tells us how to get from basis b1 to b2. And this we can then apply to any coordinate vector under the basis b1 to get the coordinates for that vector under b2. Some bases, like the eigenbasis, align the axes with directions where the transformation acts as simple scaling. So here you can see an example of how a linear transformation, which scales in two directions to different degrees, can in a first step change the basis of representation so that these directions that get stretched align with the standard basis main directions. So that in a second step, only along these directions does the space need to be stretched, which can be done by the multiplication of a simple diagonal matrix. And in a second step, making a change of basis back to our original basis allows us to align these main directions back to what they were before. This allows us to describe specific transformations using only simple operations. So rotations, stretching along the main axes, and rotations back. So an operation that's as complex as stretching in directions that don't align with axes can, in another basis, be completely described by stretching or scaling in these main directions. The change of basis is a powerful idea that shows up in techniques like the eigendecomposition, which I briefly introduced here, where we choose a basis that makes transformations much simpler. If you want to see how that works, watch this video next, or check out the full linear algebra playlist here to build the bigger picture. Let me know what you'd like to see next, and as always, thanks for watching.